So this is part 3 of lesson 2.4. So all I want us to do right now is just notice something about these animations. So on the left side, we have this kinetic friction going on, okay? The word kinetic, you've probably heard of it when you were a little kid. We talked about kinetic energy. In our last unit, the base word, especially this word kine, right? The base, we talked about kinematics, and there was this thing called kinesiology. So all that means is that this has something to do with movement, right? So if I say kinetic friction, all that means is that that's the friction from when an object is moving. So let's take a look at what this is, static friction. So if something's static, we might not know what that means right away, but if we look at the picture, we might get a sense of, hey, this is what's happening. So if we look at it, the guy's not moving. So this just means that it's not moving. Static just refers to objects that are not moving or whatever. Another way you can say this is at rest or it's still. And a student actually had a really good idea. The word stationary. Oops, I'm gonna have to rewrite that. It's a little bit ugly for me. Um, so let me rewrite that nicely. Stationary. Okay, so they said, hey, Miss Laura, look, S-T-A-T-I, S-T-A-T-I. Static for stationary. That just means it's at rest or it's still. Okay, and I guess I'll clean that up too because it kind of looks a little bad still. All right, so if you notice, let's go back to the left side, the kinetic friction. So obviously the guy is moving it. The surface, right? Let's take a look at it. It's definitely not smooth. We do clearly see ridges and bumps. And again, it's emphasized to show that, yes, that's what it looks like. But with our naked eyes, we can't detect that. But with a microscope, we could. So we definitely do know that there's some force of friction. We see that there's two vectors, a force applied and a force of friction. They're pointing in the opposite directions. It might be hard to see, but they're really the same size magnitude. So they're really the same length. Which means what? If they're the same length and that object is moving, that object is moving at constant velocity, okay? If it was accelerating, how would we know? Well, one of those vectors would be bigger than the other, okay? Now let's take a look to the right. Now we have static friction. Clearly we just said, hey, this is the friction for when objects are not moving. Again, we have the same size vectors, force of friction and force applied. However, my object isn't moving. And that should make sense because when objects are at rest, we know that our on our free body diagram, our force of friction and our force applied are the same thing and that they'll actually cancel out. Okay? So if we look at this next part, right? So we know that there's two types of friction. So we have static friction, which is just the force of friction that must be overcome to move an object that was originally at rest. Okay, this word overcome might look kind of challenging. Um, it's not. It's just, that just means that you just break through the limit. Okay, so there's this limit and you have to go past it. Essentially, that's what that is. So static just means that objects that are at rest only. Some keywords that you would see would be not in motion, at rest, still. Let's add in stationary above here, just so you can get a figure of different types of words we can see. Then our second type of friction is known as kinetic friction. So this is the type of friction that only opposes moving objects. So therefore, kinetic friction only is affecting moving objects. You will never see things at rest that have kinetic friction because it only has static friction. And so it only appears when the static friction threshold, right, this word threshold, the limit is overcome. And this happens, or how do we see that this happens? That means the object begins to move against another surface. So that moment where it goes from being at rest to moving, that means that that static friction limit has been broken and now that object is moving. So some keywords that we might see would be sliding, moving, pushing, pulling, or skidding. What I would like us to write, if it's not already written in our notes, would be the force of friction on the y-axis with our units with a capital N for newtons, and the force applied, again, with the same units, because we know that all forces have the same units. We're going to pick a different color. We're going to draw this following graph. So right here is kinetic. Okay, and then the next one, let's see, we can do it in purple, would be static friction. And then right at this peak right here, we call that the threshold of motion. So all that really means is at that point, that's where our object starts to move. So that means that we overcame static friction. Okay, so we broke the limit. All right, so at this point, you will see motion happening right up here. And if you notice, if you look across, the force of friction has to be greater right here where the star is than right here where the dot is. So in the beginning, when I'm pushing and I have to apply a huge force to the object, so think of the car, I have to apply a huge force, right? Because I'm experiencing static friction since it's at rest. Then I hit this point, right? That's the threshold of motion. So at that point, my object goes from being at rest to moving, which means I overcame static friction. And now the force that I have to apply is no longer so big because my object is already moving. And now I'm experiencing only static friction, which is a lot easier for us to move objects. So that's all the differences. So that graph is actually pretty important.